Hello everyone and welcome back to the penultimate class or the lecture of fundamentals of particle and fluid solid processing, and we were discussing about the colloids and the nanoparticles. We have seen the surface forces, the net or the resulting force, and how it impacts on the suspension that we will see today. So, for that we have introduced this suspension rheology in the last class. So, where I mentioned that the rheology is the study of flow and deformation of a matter. Now, it encompasses a wide range of behavior starting from Newtonian to the very elastic nature of the fluid. So, now the influencing parameter of this suspension rheology are typically the volume fraction of the solids, viscosity of the fluid, surface forces between the particles, and particle shape as well as its size. So, these are the critical or the main influencing parameters that we will see today, that how it actually influences the rheology. Now, foremost important thing is the surface force between the particles when it comes to the fine particles or the nanoparticles and the colloids. Now, we have seen those kind of forces, that what are the contributing forces to the surface forces. So, we will broadly mention this now as a clubbed term is the interparticle interaction. Okay. Now, to understand this influence, say we take one by one. First, let us understand the influence of volume fraction without any surface force or without any interparticle forces, which means in such scenario can happen when the hydrodynamic forces are the dominant forces. It dictates the behavior of the particles including the suspension, and there is, since we are talking about the fine particles, there is the movement due to Brownian motion. But these are non-interacting particle, and we typically say this approach to understand the behavior of a suspension is the hard sphere model. That means, when there is no interaction between the particles. So, in this hard sphere approach or hard sphere modeling, say in a Newtonian liquid, this addition of spherical particle increases the viscosity due to the additional energy dissipation that would happen, that related to this hydrodynamic interaction between the liquid and the sphere. So, as we increase the solids concentration in a Newtonian suspension, say, the viscosity typically increases. Now, Einstein proposes a relation of this suspension viscosity and the liquid viscosity, that is when it was without any liquid solid particles. Now, that expression or this expression that is mentioned here, where mu s is the suspension viscosity, mu l is the liquid viscosity, and it is related by a volume fraction of the solids, which is 1 minus epsilon, where epsilon is the voidage. Because if this is the voidage, so that means 1 minus epsilon would naturally be the volume fraction. So, 2.5 times of the volume fraction plus 1 multiplied by mu L gives us the mu suspension. Now, this expression holds true for very dilute suspension, for near about when the solids concentrations are less than 7% by volume. Now, the basic assumption that was made while proposing this expression was that these particles are far away from each other. So, there is no influence of one particle on another. So, that was the definition of very dilute suspension. Now, for that, these expressions, it has been tested by several experimental process methods, and it holds true. Now, the volume fraction of solids when it is around 10%, then the average separation distance between the particle becomes near about equal to that of the particle diameter, and that triggers the influencing of one particle to the other, or influenced of one particle the presence of the other. So, in this range, say moderately concentrated suspension, so 7 to 15% in the range, Batchelor further expanded this expression and proposed that the suspension viscosity remains still in Newtonian regime, but it does not just vary linearly like it was proposed by Einstein. So, that expression is mentioned here. So, again this has been tested and has been seen that it reasonably fits several experimental data. Now, at higher concentration than this, that whatever is mentioned here, that is near about 15% by volume, when we go above that, when we add some more solids to the suspension, then the suspension viscosity increases faster, it rapidly increases, and it exhibits shear thinning behavior. That means, its viscosity goes down as we increase the shear rate on that suspension. So, this interesting behavior, we will see that why this happens. Now, remember, we are talking about the hard sphere model or the hard sphere approach, in which there is no interparticle interaction. So, what happens here, that while at rest, this moderately suspended concentrated suspension, in the particles we will have its Brownian motion, okay, and now this Brownian motion actually dictates the suspension rheology. So, any addition of the concentration or the solids concentration in that suspension, its viscosity is dictated by that amount of the concentration. So, initially for a particular say concentration, it will have a Newtonian like plateau at the lower shear rate, and as the shear rate is increased, the hydrodynamic interactions will be higher and higher, will become more dominant than this Brownian motion, and the particles will be in a more arranged manner, or say it will be in a kind of layered state, which is also called the preferred flow structure, which is shown here. So, from a random position of the particles, it becomes more organized, and quite naturally then the viscosity becomes smoother or lower. So, this transition from a low shear rate Newtonian plateau to a high shear rate Newtonian plateau is the shear thinning behavior. So, that means at lower shear rate we have the Brownian motions that dictates the suspension rheology. As we increase the shear rate, these hard spheres, or say hard sphere means this, as I mentioned, the non-interacting particles, they are now more organized, say kind of sheets or layer, okay, and then the flow becomes much smoother. That means the viscosity goes down. So, this decrease, this transition is the shear thinning behavior. So, here it is the shear rate versus the suspension viscosity, both in log scale. So, this is what happens in case of the non-interacting particles. Now, for highly concentrated suspensions, there is no as such first principle model to predict the rheological behavior of such concentrations, but there are, like in other sections we mentioned, several semi-empirical models are available which helps to understand this concentrated suspension behavior, and one of such is mentioned here, a simplified form where This first term represents either the low shear rate Newtonian plateau viscosity or the high shear rate Newtonian plateau viscosity. And this phi max is a fitting parameter that is considered as a measure of maximum packing limit or packing fraction of that fine particles or the powders. So, such suspension under very high shear rate and high solids concentration that leads to its maximum packing fraction, what happens that the structure that was developed, or say the sheets or the layers that was developed at the high shear rate Newtonian plateau, that becomes unstable, because now here we have more solids concentration, okay, and very high shear rate. So, this what it does, it destabilizes that preferred flow state or structure. There is very large hydrodynamic interaction which leads to formation of particle clusters, which also is called the hydrodynamic clusters. And then these clusters makes the flow more difficult, which means again the viscosity goes higher, and these clusters at times blocks the flow, or say it jams the flow. So, that is called the jamming phenomenon, and this whole observation is called the shear thickening behavior. That means the viscosity is now increasing as we increase the shear rate, and this is the common occurrence in case of concentrated suspension by hard sphere approach. So, this is what something happens in schematically. So, here say below a certain volume fraction, it is Newtonian, that the viscosity does not change with the shear. Now, it is having a constant viscosity system. Now, as the shear rate increases with the concentration, so say we have this low shear rate Newtonian plateau initially, and then it exhibits shear thinning behavior followed by high shear rate Newtonian plateau, and this is all happening because of the arrangement or the rearrangement of the particles in the suspension from Brownian state to a more organized state, layered kind of state. So, this with the increasing shear there is a smooth movement of the fluid, but at a very high, so this high shear rate Newtonian plateau is arrived when it has reached this preferred flow structure limit. So, for a time being this state is not further improved, or there is no space to improve it further, which means that stage is remained for a certain time. That also depends on the particle size, not particle size, the particle type. Now, after that it again increases because this preferred state is now unstable due to the higher concentration and or this happens due to high shear rate. So, we can see that this state becomes more narrower, the range becomes more narrower as we increase the concentration, that this high shear rate Newtonian plateau, and the onset of shear thickening regime goes higher and higher. So, these lines are basically having a zone or it is showing a zone of shear thinning, and this is the shear thickening zone. So, which means here in this region we can see that the viscosity is going down, and in this region we can see the viscosity is going higher. So, this is all happening again for the particle rearrangement in layers, and after that, that layer is broken due to the high hydrodynamic interaction, and that leads to the cluster or the aggregates of the particles, which called the hydrodynamic cluster. It then blocks the flow, it makes the flow more difficult. Now, when there are repulsive force, now the particles, we are now talking about that the particles are there in the suspension, but the interaction between them is repulsive in nature. So, then what happens? It similarly behaves as of the hard sphere approach or the hard sphere behavior when they are separated at a larger distance, that in the range of repulsive force, because then there is proper dispersion is there, because we have seen that this attractive force tends to form aggregates. Now, if the particles are separated at a long range repulsive force, then these are more dispersive in nature, or there is, say, I would say, more dispersion is there, uniform dispersion can happen with these repulsive forces. And this is indeed true for low volume fraction or relatively large particle, because at the low volume fraction these particles are separated far away from each other. Once we increase the volume fraction, there is the overlapping of this repulsive force field, and that leads to the increase in viscosity compared to the hard sphere. So, even say there is a same particle and same volume fraction in two suspensions, in one case we are considering repulsive force or say the surface force included phenomena, the other one is simply hard sphere method. In both the cases, in the second one there will be a reduced viscosity, because we have not considered there the particle interaction. So, here due to this repulsive force and its overlapping, there will be enhanced viscosity compared to that of the hard sphere of same material and same volume fraction. Now, in very small particles, say 100 nanometer or less, the average interparticle distance even at moderate volume fraction is in the order of the range of this repulsion. That means, in this case we will have enhanced or increased viscosity, because the repulsive force fields are overlapping. So, that leads to increased viscosity. Now, also for dilute suspension of repulsive particles, we will have this larger viscosity than these hard spheres, because of this additional viscous dissipation of the fluid flow through this repulsive region around the particle. Now, such phenomena in case of suspension having electric double layer is called the primary electroviscous effect. That means, even this is the very dilute suspension of the particles, there would be larger viscosity, although the behavior I have mentioned as similar, but there would be the larger viscosity compared to the simple hard spheres, because of this additional viscous dissipation that would happen in the repulsive force field. So, a suspension having electric double layer, this phenomena is called the primary electroviscous effect. and the total drag on the particle and the EDL is greater than the drag that was considered or that happened in case of simple hard sphere model. However, there is insignificant increase in viscosity due to this primary electroviscous effect. Now, when the concentration goes higher with such particles, there is significantly elevated viscosities compared to that of the hard sphere model of same volume fraction and same material due to this interaction between the overlapping EDLs. Now, in the ideal suspension, the EDLs are overlapping, that has tremendous repulsion. So, this when we try to push them, the particles closer, there is the secondary electroviscous effect that this electrical double layer must be distorted in order to keep them in contact, and that phenomena is called the secondary electroviscous effect. So, the influence of repulsive force in suspension basically can be also measured in terms of effective volume fraction of the particle. What is effective volume fraction of the particle? It is the volume fraction of the particle plus the fraction of the volume occupied by the repulsive region around the particle. So, this EDL layer, say. So, for example, in this schematic, this what could have been the actual particle arrangement and the voidage calculations in between these. But with the repulsive forces, there is, or say the EDL layer, there are this layer which actually occupying some virtual space. So, this total volume becomes the effective volume than the actual volume of the particles. So, the volume fraction of the particles plus the fraction of volume occupied by the repulsive region around the particle is the effective volume. Now, the previous expression that we have seen for the concentrated suspension, if this expression, so this one, if it is replaced the phi with the phi effective, it actually predicts the behavior of such suspension. And here this schematic shows that the volume fraction and relative viscosity, and we see that this is actually the volume fraction and this is basically the effective volume fraction. So, for a relative particular velocity, we have basically higher effective limit volume fraction. So, for actual volume fraction, we have higher effective volume because of these layers or the force field that is there. So, how does it matter? So, say this problem statement, you have to calculate the effective volume fraction for a suspension of 150 nanometer silica particles at 40 volume percent solids in a solution of 0.005 molar initial solution. So, this is say the actual volume fraction of this silica particles of known diameter in electrolyte. What is the effective volume fraction? So, how do we calculate such scenario? If we use this knowledge that we have just seen, that the phi effective is basically the volume of solid plus the excluded volume, which means that we did not take into account, but which is there when it is immersed in the electrolyte, divided by the total volume. So, for particles stabilized by the EDL repulsion, excluded volume from the range of repulsion can be estimated by the Debye length that we have seen earlier, that it is a measure of the range of this EDL force as well as its thickness. So, inverse Debye length, we have seen this as a function of the salt concentration, and for monovalent salt this was the relation that we have seen earlier, and it provides this inverse Debye length. So, for 0.005 molar NaCl, we have this as the kappa. So, which means the Debye length, the inverse of that is 4.3 nanometer. Once we know the Debye length, now that means a particle would be in contact with the other particle, including its Debye length, the thickness of the EDL. So, which means the effective particle size, say for a single particle, this would be the total diameter or the total size of the particle. So, which means on both the sides we have the thickness of 4.3 nanometer. So, the effective diameter becomes its original diameter, which is 150 nanometer plus 4.3 plus 4.3, and such a manner all other particles are there. So, for only one particle, if we consider only one particle, then the volume of a single particle is this one. But the particle with the excluded volume, excluded means excluded during the consideration of calculating its volume fraction, would be this one, and the ratio of these two is basically we have the effective volume fraction. So, this is how this knowledge is useful in this case. And now we will see what will happen in case of attractive forces. So, after hard sphere approach, we have seen if the particles are repulsive in nature, it behaves similarly. But what will happen in case of attractive particle? So, this we will continue in our next class, and we will see that how the overall influence of these forces happens on a particular case, see the sedimentation, which is the liquid solid separation, that is one of our intention initially, and how this knowledge helps in that from that perspective. So, we will be continue our discussion in the next class with these attractive forces. Till then, thank you for your attention.